Okay, we're gonna start. Everyone's been muted for now. I'm Jessica. I'm this year's president, and I want to welcome you all to our first lecture at the new earlier start time of 7 p.m. If you are a member, you should have received an email last week informing you about the new start time and also a link to a poll about the change. If you haven't completed the poll and you have time, please go complete it. It really takes about 2 minutes. It's very easy, but it will help us. And if you have any questions or comments about the lecture or the new start time, feel free to email me. My email address is president@sfaa-astronomy.org. And I'll also put that in the chat bar in this window. And a couple quick updates. We are very close to getting our permits for Mount Tam this year. We are in the final stages. It's been a lot of back and forth emailing with the state parks. The only thing that we are still uncertain about is when the state parks will actually open for events. So hopefully June, but it might be July. And we have a couple of really good dates on the calendar. And as soon as I find out, we will let all the members know via email and newsletter and Facebook and all of our social media. I know we've all been looking forward to getting back up on Mount Tam. And then if you didn't attend the amazing class taught by Bill Kircher, our vice president on observing basics, he will be giving the third class in the series next month. For that date, we will email everyone and let them know. And if you would like to review the first and second classes, those are up on YouTube. And they are wonderful and they're very informative. So that is it. And again, I will put my email address in the chat window if anyone has any comments or questions about the club in general or our new start time. And with that, I will turn it over to Linda to introduce the speaker.
Okay, hello everybody. I'm so happy that you're here and so happy we'll all get to hear Stella Kafka soon. But first, I'm going to introduce briefly the next 2 months' speakers. On Wednesday, June 16th, again, we'll be open an hour earlier. We'll be starting the lecture at 7. Globular clusters and the role of binary star dynamics. This is going to be presented by Dr. Adrian Kuhl, Professor, Physics and Astronomy at San Francisco State University. Dr. Kuhl will share results from her research on globular clusters, which are ancient and fascinating structures. She and her students search for binary stars in globular clusters using space-based observatories. And she will also discuss her founding of the Organization of Astronomy and Astronomy Educators named Astronomers for Planet Earth. That's June 16th. On Wednesday, July 21st, beginning again, 7 p.m., fast radio bursts, electromagnetic pulses from cosmologically distant neutron stars with 100 gigatesla magnetic fields. This is something that will be discussed by Dr. Roger Blandford, Stanford University, CAIPAC. He's a professor of particle physics and astrophysics. For over a decade, radio astronomers have been observing millisecond pulses of intense radio emissions. They now appear to be associated with strongly magnetized neutron stars called magnetars. The rapidly developing observational picture will be summarized in Dr. Blandford's presentation. Tonight, variable stars and their stories will be so interesting. Dr. Stella Kafka will be speaking, as some of you already know, from Cambridge, Massachusetts, and we thank you so much for staying up late. Dr. Stella Kafka is the executive director and CEO of the American Association of Variable Star Observers, AAVSO, which was founded in 1911, an international organization focusing on engaging professional and amateur astronomers in science. Within the auspices of AAVSO, Dr. Kafka is working toward enabling individuals from all backgrounds to actively participate in research projects, building a community of science-savvy citizens who work collectively to understand some of the most dynamic phenomena in the universe. Variable stars have always been the most intriguing and fun targets for observers. Dr. Kafka will introduce aspects of stellar variability and their significance in astrophysics. And finally, you'll learn how you can participate in variable star observations from your backyard. We welcome your presentation, Dr. Kafka.
Thank you so much for having me. Thank you for spending this evening with me. Let me start by finding the right screen to share. How about that? Can you see my screen?
Yeah.
Thumbs up, thumbs down, maybe, maybe not. All right,
Yes.
awesome. Thank you. Thank you very much. All right, so as mentioned, I am Stella Kafka, the Executive Director of the AAVSO, and today I want to talk to you a little bit about variable stars, just to give you an idea of what they are, why we're observing them, and perhaps whet your appetite if you want to observe with us, join us. But let me start by reminding you that the AAVSO was formed out of a Harvard College Observatory in 1911 to coordinate variable star observations for Observatory Director Edward Pickering. William Tyler Olcott, an amateur astronomer, regularly sent Pickering his variable star observations after hearing Pickering discussing variable stars at a talk. In June of 1911, Pickering published a list of variable stars that needed to be observed and people he thought would be interested in taking part. The moment is often referred as the embryo of the AAVSO, as Olcott and his other amateur astronomer colleagues began observing and submitting their findings to help advance Pickering's research. As such, in principle, the AAVSO was the first association that was founded in order to connect professional and amateur astronomers and help them collaborate on scientific projects. This is actually a snapshot of our incorporation document to the state of Massachusetts, stating that the AAVSO was founded for the purpose of promoting variable stars and kindred objects. Even at the beginning of last century, our forefathers realized that there may be more types of variability other than stars, and they wanted to make sure that the AAVSO is involved with all types of scientific projects that would be of relevance and interest to our observers. Well, since 1911, 110 years ago, we have really evolved. Now we are truly international. We have individuals from 50 different countries, about 6,000 people who are interested in variable stars. As a consequence, we have a very diverse community. This translates to serving people with different needs, different priorities, different professional preparation, different habits and cultural backgrounds, who are united under the international umbrella of astronomy. We have individuals who are interested in using variable star data for their research projects. We work with educators who introduce astronomy to their students. We collaborate with a very dedicated group of volunteers. We communicate with astronomy enthusiasts who are very interested in learning about new science discoveries in astronomy and support citizen science. And of course, we have our observers, those who acquire data through their telescopes, CCDs, or DSLR cameras and share this information with a wider international community through the AAVSO databases. You know, when I was preparing this presentation, I was looking at the first instance when a variable star was mentioned in literature. And I stumbled upon this paper that you can actually download for free from arXiv. The researchers in this paper present evidence that Algol, the raging one, is mentioned into the Cairo calendar, which was a religious book in ancient Egypt. Not only that, but ancient Egyptians knew 3,000 years ago that this star was changing with time in a repetitive manner, and it had a period of 2.8 days. So variable stars are not exactly their recent discoveries. They've been known for a long time. But before I start telling you more about that, let's play a game. I want you to unmute yourselves for this game. Come on, what day is it today? It's Wednesday afternoon. Let's make it fun. And the rules of the game go as follows. Let's say that this is a part of the night sky. Every dot that you see here is a star. Bigger dots are brighter stars, smaller dots are fainter stars. Yes? I want to see thumbs up or nod. I can see you. Awesome. Now, I want to to characterize each star by a number that represents its brightness. And because it's my game and I make the rules, I'm going to do things backwards in the sense that I'm going to characterize the brightest stars with the smaller number and the faintest stars with a larger number. So according to those rules, this one is number 51. This is the brightest star in this part of the sky. This is number 91, number 64, 61, 85, 75. Yes? Yes, no? All right, cool. So here's a star here that does not have a number attached to it. And I'm going to name this star Mary because Mary is one of my best friends and I really love her. So she is a star. So with respect to the rest of the stars here, what kind of number would you assign to Mary to assess its brightness? You should unmute yourselves because this is supposed to be interactive. Silence. Okay, so is it brighter or fainter than this?
Fainter.
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 Brighter or fainter than this?
Brighter.
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 Brighter. How about this? Brighter or fainter?
Brighter.
Brighter.
Brighter or fainter than this?
Fainter. A little bit
Fainter.
fainter.
A little fainter,
It's a
right?
63.
So let's give it a
62.
63. Sure, sure. Okay, so I went out a week after. Here's the same part of the sky, and here's Mary tonight. What number would we assign to Mary?
94.
94? So again,
Yeah.
the same procedure, right? Is it brighter or fainter than this? I'm going to give you
Fainter.
It's fainter. Brighter or fainter than this?
Fainter.
Fainter.
Fainter. Brighter and fainter than this?
Little fainter.
How about this one?
Fainter. About the
Depending on
same.
the resolution of your screen, right? It may be
Very
fainter or the
close.
same. So let's give it 91, 94.
About the same.
About the same. Here's a third
Yeah.
night. Here's Mary tonight. What's the brightness of Mary tonight? What number are we going to assign to Mary?
64.
63.
Lower, higher, 70.
70, yeah.
64 and a half.
I go with 70.
So again, brighter or fainter than that?
Fainter than 51.
Fainter.
Fainter 51. How about brighter or fainter than 91?
Brighter.
Brighter.
Brighter than 91.
Brighter.
How about 64
Almost.
But fainter.
A little brighter.
or 75?
Close.
Yeah,
Somewhere
close.
in
It's the
between,
same.
right? It's just it's
Yeah.
not
It's in
clear,
between.
but it's in between. Well, Mary is a variable star in the sense that every time we go out and observe it, its brightness is changing with time. And congratulations, you just built your first light curve. A light curve is a plot of the brightness change of a variable star with time. And actually, in principle, we can build light curves for all the stars in the night sky. The difference is that variable stars' brightnesses change and non-variable stars' brightness don't change. And you know, we can do, and everything that we know about variable stars I'm going to talk about today is based on light curves. The procedure that we need to take data is exactly what you just went through right now. You take a snapshot of the star of your interest and you compare its brightness with the stars in its vicinity using your binoculars, your DSLR cameras, your telescopes, etc. Here's another example. So again, variable stars whose brightness is changing with time, within timescales we can measure with respect to stars whose brightness is not changing with time. This one is a movie that was generated with 4 different digital images taken the same night. Actually, they were taken back to back. And actually, if you pay attention, this is a globular cluster, it's M3. It's a beautiful, beautiful, very dense object. If you pay attention, most of the stars don't do much. They're just hanging out there. They're nice and bright and pretty. However, if you pay closer attention, you'll see that some of those stars are blinking. Can you observe the variables? Let's see, I'm gonna go to this screen. Here and here, and maybe here. Or here. You know, if we had time, I would ask you how many variables can you count within 30 seconds? But the bottom line is that this is what we mean by variable stars. Stars whose brightness is changing every time we observe them. And this is just an example of a real life image that was taken of an object that has a lot of those variable stars. So variable stars have all types of classification. In principle, there's a zoo of them. There are many categories. The formal classification, they're presented here. And in principle, there are two major categories. They are the intrinsic and the extrinsic variable. Extrinsic variable are those who seem to be variable because of their appearance. There's something going on in their vicinity. In intrinsic, the cause of variability lies in the interior of the stars. We will discuss aspects of these categories, focusing on just representative classes. And also please note that they're not exclusive clubs or classifications. Stars can belong in more than one category, and we classify them based on the most pronounced characteristic. But first, I would like to reclassify them just for today, because it's much more fun this way. And I am going to refer to them as good, bad, and explosive. So I'm going to change the title of my talk today. Instead of variable stars as stories, we're going to talk about variable stars, the good, the bad, and the explosive. And I'm going to start with the first category, the good ones, that are here. Good ones are the periodic variables. These are stars that do something repetitively. Variables that seem to change in brightness in a much more constant way. They do the same thing again and again, and actually you can predict their behavior before you observe it and then go take data to confirm it. And here are the two most common ways of variability: binary stars and pulsating variables. Starting with binary stars, are two stars that are tied together by gravity, so they can't escape. And all they do is dance around each other together. They're gravitationally tied and move around their common center of mass. This is a cartoon that showcases this kind of motion. Star 1, star 2, their common center of mass, and they're just moving around. And this is an artist's rendering of how they should look like in the universe. Actually, more than 50% of the stars in our galaxy, and actually some say up to 75%, belong in some type of binary system. So these are some of the most common variable stars in our galaxy alone. This is an example of what we call a visual binary, and I'm pretty sure that you've seen it before, Sirius, right? How many of you have actually observed Canis Major? Have you seen Sirius?
Oh, yeah.
Yeah.
Yeah, have you seen the two stars in Sirius?
No.
Separation is just only 20 astronomical units. So imagine two stars in a distance that is similar to the distance between the sun and Jupiter. So they're very close together. Their orbital period around the common center of mass is only 50 years. So if 50 years ago, you went out and took a look at the configuration of the two stars, and you go out tonight, you'll be able to see it at the same configurations. They move around the common center of mass. We don't have many visual binary systems that we can actually do that. Here's an interesting fact. The two stellar components are very, very different. The Sirius A is an A star. So it's a star that is more massive than our sun. It's a very massive star. So it's a really very bright star. Sirius B is a very special type of star. It's what we call a white dwarf. And as a white dwarf, it's a star that has a mass equal to the mass of the sun, squeezed to the size of the Earth. So you can imagine it's an extremely dense star and extremely, extremely hot star. So although in optical wavelengths, Sirius A overshines Sirius B, if we were to take a picture in X-rays, Sirius B outshines the system. It's much, much brighter than Sirius A. These are real images, actually. Most of the time, though, we know that a star, a bright dot in the night sky is a binary star system when the orientation of the orbit is just right. The plane of the orbit is at the same plane as your line of sight. So as one star passes between the observer and the star, the observer sees a dimming in the system's collective brightness, what we call an eclipse. This is a cartoon showcases a binary star system, its brightness out of eclipse, and the dip in the light curve that is caused by one star covering part of the light of its companion. Those stars are extremely important because by measuring the duration of the eclipse in the light curves, we can find out the size of each star, the diameter of it, which is actually impossible to measure otherwise. And actually, Algol, remember the star that I told you about that was known to ancient Egyptians, was one of those stars. Ancient Egyptians knew about eclipsing binaries, knew that Algol was an eclipsing binary, and they knew that the period, the time that it took for the two stellar components to go around the common center of mass was about 2.8 days. Now, here's the cool thing. The same technique that ancient Egyptians used 3,000 years ago to study Algol and actually figure out what the period is, the technique we're using right now to study eclipsing binaries, which are some of the most valuable stars in astrophysics, are actually used in order to detect exoplanets. I'm pretty sure that you've heard about the transit method, right? The exoplanet transit method. Exoplanet transits are pretty much when you have a star and a planet, and the planet is actually passing in front of its parent star, causing a small dimming, a small eclipse in its brightness. That's all there is to it. A technique that is known for 3,000 years now. We just have better equipment and are able to do something like that. So this is, say, a solar type star. You can see in this cartoon the effect of a smaller, a large planet as it passes in front of it. And here's another example. If you have a solar type star and a Jupiter-sized planet, this is a light curve that can be taken from Earth with an 8-inch telescope. You can definitely see the transit. You can see the eclipse as the planet is passing in front of the star. If you have a Neptune-sized planet in front of a solar type star, you can see a much more shallow eclipse, but you can still observe it from the Earth. You have good conditions, et cetera, et cetera. Now, I have to convince you that there is an Earth-sized planet somewhere here, an Earth-sized dot in front of the star. It's really difficult to see. And the effect on the light curve is that red little line, pretty much nothing. You cannot see it from the Earth. And that is why, in order to detect Earth-sized planets, we really need to go to space. We really need to eliminate the noise that the Earth's atmosphere is introducing in our observations. Now, another category of periodic variables are what we call pulsating variable stars. These are single stars. These are intrinsic variables, meaning that the cause of variability lies in the interior of the star. Let's take a step back. Stars are huge balls of gas, right? Those balls of gas are controlled by two main forces. There's the force of gravity that keeps everything together. Gravity tries to push all gas from a star, all atoms of that gas, as close together as possible, right? The second force is what we call gas pressure. At the very center of each star, we have a whole bunch of say that we have a nuclear reactor, much better. And in this particular case, most stars are converting their hydrogen into heavier elements like helium, lithium, et cetera, et cetera. Now, as a result of those nuclear reactions, radiation is created that tries to pull all gas layers apart. So gravity tries to push gas layer inwards. Radiation pressure from the inside, it's like the radiation on top of your heater, heat, is trying to pull everything apart. And at some point, there is a state where the force of gravity is balancing the force by gas pressure. And this allows the star to be in some kind of an equilibrium, what we call hydrostatic equilibrium, right? This is how most stars spend most of their time. Now, at some point though, hydrogen at the very center of a star is exhausted. And this equilibrium is disrupted. and then a battle starts between gravity and gas pressure trying to dominate each other. Here's an artist's rendering of how this process looks like. Here's your regular star in hydrostatic equilibrium, just hanging out in space, just rotating around its axis. And at some point, hydrogen is being exhausted in its interior. Now, when gravity wins, the gas is compressed. When gas pressure wins, the gas layers are pulled apart. And this is continued for a while until the star moves in the next phase of its life. But during that phase where the hydrostatic equilibrium is being disrupted, the star pulsates in and out, literally moving in and out. So we're talking about a star who is changing in size with time, and this is reflected in the light curve. Periodic brightnesses pretty much have this very characteristic shape. Just imagine a ball that's bouncing in and out. So when we see a light curve like that, we know that a star is a pulsating variable. Now, here's a kind of pulsating variables that are really very important. And at that point, let me tell you the story of Henrietta Levy. This young lady worked at the Harvard Observatory back in 1911. Actually, she was there in 1911. Henrietta Levy was there at the beginning of the AAVSO. But back in 1912, she was studying photographic plates. She was one of Pickering's computers. And she was actually studying plates that were coming from this little smudge in the sky. If you ever go to the Southern Hemisphere, look up. You can see the two Magellanic Clouds, which are pretty much satellite galaxies of our own. And they're really beautiful, very spectacular. This is a large Magellanic Cloud, and this is a small Magellanic Cloud. So while she was studying the small Magellanic Cloud stars and she was cataloging, she found a huge, huge number of Cepheid variables. Cepheids were known, but they were considered to be very rare. And suddenly she started finding a huge number of them. Now, all of them seem to be at the vicinity of the galaxy. And she actually made an assumption that all of them were actually more or less in that galaxy. So their distance from here was the same. Now, after measuring the periods of the Cepheids and the relative brightness of each one, she found a relation between the period and apparent brightness for all the stars, in the sense that stars with longer periods were brighter than stars with shorter periods, making the reasonable assumption that small Magellanic Cloud is far away. And because all of them were kind of concentrated there, they were more or less in the vicinity of the Magellanic Cloud. She defined the relationship between the period, the absolute brightness, that helped actually measure the distance to the galaxy. This is what we know as Levys Law right now, and it's established as part of the distance ladder in astronomy. Have you ever wondered how we know how far away stars are? It's not that you're going to take one side of a yardstick. I'm going to take the other star of a yardstick. I'm going to go to a star and we're going to measure the distance. We are using properties of variable stars, in this case, Cepheids, in order to figure out how far away different parts of our galaxy are. Cepheids are very, very commonly found everywhere. So even right now, it's a very active research field trying to identify them and study Levys Law and apply Levys Law. Now, enough with the good variables. Let's go to the bad ones. And this is a prototype. Anyone recognizing this star? Anyone recognizing this star?
Yeah, our sun.
Yes, it is our sun. It's our own star. It's our sun. Our sun actually, the first person who studied the sun through a telescope was Galileo Galilei. about 400 years ago, more than 400 years ago. And legend tells us that Galileo took a piece of glass, like the one that you have on your window. He put it on top of fire and he collected smoke. And then he put this smoke in front of his telescope, using it as a filter to cut some of the starlight in order to observe the sun. Well, Galileo died blind. Should I say that again? If there's one thing that I would like you to take from this presentation is that we're not supposed to observe the sun directly with any means other than special filters. Galileo really destroyed his vision. However, he left a really very rich archive of observations of the sun, of the outer atmosphere of the sun. He was the first to actually say that the sun is not a perfect object. It's not a perfect sphere. It consists of dots, and those dots are attached to the atmospheric layer of the sun and are rotating with the sun itself. Now we know, as the sun is the closest object to the Earth, we know that it's definitely not a perfect sphere. It's not a perfect object. It's actually a very active, a very dynamic place. It has all kinds of phenomena. Other than spots and spicules, it has prominences and filaments, coronal mass ejections. It's really very dynamic. This is a compilation of real images, real pictures of the sun. It's so nearby, we can actually take photographs. And everything you see here is because of the sun's magnetic field. Now, magnetic fields in the universe are very complicated. They never come as a north and south pole. So what happens here and is the cause of all these phenomena are two different things happening at the same time. The first is the fact that the sun does not rotate uniformly around its rotation axis. The sun is not a solid sphere. The sun is a gas, right? So the equator of the sun rotates faster than the poles. This is possible, again, because the sun is not a solid body. And this is a phenomenon that we know and we now call differential rotation. And it is known to exist in other stars as well. The second phenomena is that the sun's global magnetic field, north-south pole, is attached to different atmospheric layers. Now, because of differential rotation, solar magnetic field lines, which are attached to the sun's atmospheric layers, moves faster in the equator, rotates faster in the equator than it rotates up at the poles. As a result, it has small, how would you call them, knots that actually are twisted locally on the surface of the sun, the atmosphere of the sun, and they emerge as localized dipoles. So we have the differential rotation and the solar magnetic field. Why does this matter? Because at the point where the magnetic field emerged from the photosphere of the sun, the magnetic pressure, the magnetic field lines suppress the gas at that particular point. So this area looks darker than the surrounding photosphere. And this is what a sunspot emerge. This is how it looks like when we observe it. It looks like a sunspot. Now, why am I mentioning that? Because sunspots are attached to the photosphere of the sun. As the sun rotates around its axis, spots come in and out of our line of sight, causing differences in the light curve. So in principle, by observing those spots and how fast they rotate in and out of a line of sight, we build a light curve and we can say how fast the sun is rotating. Or if we go to other stars, we can actually observe those spots as they move around the photosphere of the star and define a rotational period of the star, figure out how fast the star spins around its axis. Why is that important? Well, we have discovered that there is a relationship, a very unique relationship between how fast a star rotates, how active it is, how big the spots are, and how old it is, in the sense that younger stars have more spots, more activity, and rotate faster. And this is what we call the age-activity rotation relationship. So a star that is about 100 million years old will have bigger spots, it will rotate faster than a star like our sun that will have smaller spots and rotate much slower. This is how we know how old stars are. Have you ever wondered, how do we know the age of stars in the universe? It's not that they come with birth certificates. It's not exactly easy. This is how we do it. We actually go and observe how fast they rotate. And that's why it's, again, a very active source of research right now. How fast they rotate, and we calibrate the rotation period and the activity, the brightness level, the brightness change, sorry, the differential change with the age of the star, and we assign an age to it. Yes? Cool stuff, right? From variable stars. All right, let's go to the explosives, because they're some of my favorite ones. These are stars that I like studying, and I'm going to focus tonight only on one category. We're going to talk about cataclysmic variables tonight. Now, these are binary star systems where one component is a main sequence star. Like say that a star that is a little less massive than the sun, right? Is this one. And its companion is a white dwarf. Remember what we said about the white dwarf? It's a very dense star. It's a star that has the mass of the sun all the way squeezed to the size of the Earth. What that means is that if you put them really together, very close to each other, closer than the distance between the sun and the Earth, then the white dwarf's gravity dominates and it's going to start eating material from its companion. So pretty much this is stellar cannibalism in action, literally one star eating the other. Now here's another little detail. Those stars, the binary stars' orbital period is less than 10 hours. So they make one revolution around the common center of mass in less than 10 hours. In comparison, the Earth is moving around the sun. What is the Earth's period around the sun?
A year.
Thank you. 365 days and some change. So just imagine those things spinning around the common center of mass. Material does not go directly from one star to the other. It actually takes a detour and forms a siphon around the white dwarf, what we call an accretion disk, and it spirals in to get on the white dwarf's surface. So the system pretty much is quite complicated. It's a star that is being cannibalized. There's a tiny, teeny, tiny white dwarf right here at the center, and an accretion disk that is pretty much the way that materials transfer from one star to another. So as in humans, when we eat quickly, we burp. We observe burps in those stars as well. This is what we call outbursts. And those outbursts are instabilities on the accretion disk that pushes material on the white dwarf in very regular time periods. So this is pretty much a light curve, an AAVSO light curve, brightness variation with time, taken with binoculars, visual data, your eyes, nothing else, and showcase this star outbursting as material is pushed on the white dwarf from time to time. Now, there are systems in which the white dwarf is eating a lot of material really quickly. I hope you've had dinner a while ago. What happens when you eat too much too quickly?
Tummy ache.
What is the result of a tummy ache? Sometimes
Vomit.
you throw up. Well, believe it or not, this is what's happening in the stars as well. Material is accumulated on a layer surrounding the white dwarf. The white dwarf does not have time to digest it. It doesn't have time to mix the material with the rest of it in its interior. So in that particular layer, pressure and temperature increases as materials accumulated nonstop on the white dwarf. And it reaches the point where the system goes what we call a chain of reactions, thermonuclear runaway. That leads to an ejection of the outer layer of the white dwarf. So in principle, the white dwarf throws up, literally. But this is what we call a nova eruption. So a nova explosion is the outcome of a white dwarf that has consumed a lot of material really, really quickly from its companion. It didn't have the time, or the processes were not as efficient to mix it with its interior. And as a result, the blanket of material that was created outside its atmosphere erupted. The nova eruption, this is a light curve again, an AAVSO light curve in three different filters. There's visual as well in here of a nova that went off in Scorpius in 2015. It showcases this intense increase of brightness as the nova erupts and a much more smooth decrease in the light curve. These are some of the most popular targets for AAVSO observers, exactly because some of them are extremely bright. This one reached 8th magnitude. There is a nova in Cassiopeia right now that reached 5th magnitude last weekend. And right now it's at 7. So you should be able to observe it with a pair of binoculars if you have dark skies. You can find more information on the AAVSO web pages if you're interested in that. What's really interesting though is for some of those objects, when they happen nearby, we can actually take pictures. This is a picture, an image, a real image taken by the Hubble Space Telescope of a nova that went off in Cygnus in 1992. To be clear, you cannot see the stellar components. The two stars are buried somewhere in here. There's lots of really hot gas at the center. But what you see is a ring of material that is happening as material expands, gets out of the system and expands in the interstellar medium. So it's a very beautiful, pretty picture right there. So, you know, as in humans, novae never learn. So they keep eating and they keep erupting. We know of certain systems that have shown more than one nova eruption, and this is what we call recurrent novae. This is an example of a recurrent nova. Forget about this dot. This dot is just an irrelevant star. If I could actually cover it. The nova is here at the very, very center, and it was first observed in 1890. So we have more than 100 years of observations. And what you see here is material that was left over from all the subsequent explosions from the white dwarf. So the first eruption that we observed, right, was 1890, then one in 1902, 1920. It seems that every 20-ish years, there's one eruption there. 1944, 1966, then skipped one, and 2011. And believe it or not, right now there is a bet in the astronomical community on when the next eruption will happen. So please join the fun. We have no idea. We're waiting for TPICs to go off. However, there are times where the white dwarf does not eject its layers. It keeps growing in mass. It finds a way for the process to be very efficient. So it eats material and it's growing in mass. And at that point, it's increasing its own mass, right? And it reaches 1.4 solar masses. What happens in 1.4 solar masses? The core temperature of the white dwarf is sufficient to ignite carbon fusion. That results in a different set of thermonuclear reactions that result in an explosion, what we call a supernova type 1a, that completely destroys the white dwarf. The system is dead, the white dwarf is done, but as a result, this eruption enriches the interstellar medium with all kinds of metals, such as silicon, argon, calcium, titanium, vanadium, chromium, nickel, and cobalt. So this is a way of forming heavier metal, heavier than carbon, in the interior of a white dwarf indigestions. Actually, as it eats a lot of material and reaches 1.4 solar masses, Chandrasekhar mass limit. Not only that, a supernova, this type of a supernova, at its maximum is extremely bright. This is an example, a real picture, actually, a real image of a beautiful spiral galaxy. You can see the center, most likely there's a black hole, and this bright dot here at the outskirts is a supernova. So sometimes the result of this explosion can be as bright as the host galaxy. And not only that, this type of supernovae happen in all kinds of galaxies, both elliptical and spirals. Now, why is that important? Why am I even mentioning it? These supernovae are standard candles. A standard candle is an astronomical object that has a known absolute brightness at maximum. In this case, because supernova 1As are the same events, so they are the explosion of the white dwarf when it reaches 1.4 solar masses, their absolute brightness is the same for all events. So this is pretty much a compilation of light curves of a whole bunch of supernovae. Its different color represents a different event, and you can follow it all the way. They all fall on the same curve. They're exactly the same. They're expected to be the same. So if it looks like a candle here, it will look like a candle up there. If it looks like a light curve like this nearby, it's exactly the same light curve, very far away in the universe. And also, this is actually a sample spectrum, just showcasing that all kinds of elements that are being created as a result of this kind of supernova, as we discussed before. Now, this is very important for astronomers because if we know the absolute brightness of all events and we measure the apparent brightness, how bright the star looks from the Earth, we literally plug in those numbers in this equation and we can define the distance to the supernova. And exactly because these objects are really very faint, they can get us to the outskirts of our galaxy cluster and to other galaxy clusters. They're a very, very important step in the distance ladder in astronomy. So we can actually use, we do use supernova type 1A in order to measure distances really further out than Cepheids can actually indicate. Now, not only that, if you know the distance to the host galaxy and you measure how fast the host galaxy moves, what we call a redshift, you can do cosmology. So because of that, for the first time, we managed to figure out some fundamental properties of our universe, such as the universe expanding. Not only it's expanding, but it's also accelerating. And there is this magic thing called dark energy that is driving this acceleration. And just in case you were wondering if that's important or not, 2011, the Nobel Prize in Physics was awarded to two astrophysics groups. Actually, one of them is at Berkeley, UC Santa Cruz, is your side, who use supernova 1A properties to probe the universe. So the Physics Nobel Prize in 2011 was awarded for the discovery of the accelerating expansion of the universe through observations of distant supernovae. So this highlights the importance of studying supernova, and truly, all we know about the distant universe is based on this type of studies. And of course, the outcome, the cosmological outcome was confirmed with other methods, but this was the first important indication of the future of the universe, and that's why people keep observing them. Now, in the limited time that I had with you, I hope I gave you just a glimpse of what's out there. Is it all? Of course not. This is just a small part of the puzzle we're trying to put together to understand the universe. And you know something? We are explorers. As humans, we are explorers. Every time we look up, we look out, we look deep in the universe, and we use light, and we're analyzing light to probe the mysteries of the universe, to understand where we're standing, to figure out what our place is and what is out there, how it works. And since we can't actually take the USS Enterprise and boldly go where no one has gone before, and actually, I wish I could join Starman on that Tesla some years ago, we are using our telescopes, we're using our equipment to be able to take a picture, to connect with the universe and try to understand it. So what I would like to do from here on is to give you some ideas on how you can start your own program and learn a little bit more about variable stars by using AAVSO resources that are pretty much freely available on our webpage. First thing first, if you want to learn more about variable stars, we have a plethora of observing sections that are focused on different types of stars, some of which we have discussed tonight, but you can also see long period variables. You can see the sun. The sun is a variable star. Most people neglect. And actually, it's your most valuable educational tool, because observations of the sun with the proper equipment and showcasing the sun with the proper equipment does not require a whole bunch of high school kids, for example, to be in the middle of the dark, in the middle of nowhere with an adult they don't know. So I do recommend, if you have access to a school, just take your solar telescope and show them how the sun looks like. So exoplanets, high energy network, gamma ray bursters, all kinds of crazy things that give away gravitational waves. But also we have observing sections that have information on how to observe. Telescope, instrumentation and equipment, cameras, filters, telescopes, mounts, anything you want to know about your gear from beginning to really advanced. So what I'm trying to convince you here is that if you can do this, if you have a pair of binoculars or a telescope, you don't even need to have a CCD camera. If you have a DSLR camera, you take pretty pictures, you can definitely do this. So here's a very short tour of our webpage. This is what you hit when you get to our first webpage, to our new webpage. And if you want to get started, there's a little drop-down menu here where you will find all kinds of information, from what variable stars are, tutorials, manuals. If you need a mentor who can actually, a person who can help you get your program started, and actually a link to our how-to videos, which are actually helping you, giving you more focused information on specific aspects of observational astronomy. On our webpage as well, you will find all kinds of other resources that you should use, actually, and you can just do it without becoming a member. Our forums, these are so valuable for exchanging of ideas, or if you have a question, any question, there's no such thing as a dumb question. I have this kind of filter, does it work? I have this kind of gear, how do I use it? How do I get started with my binoculars? I have this kind of sky and this challenge around it. My telescope doesn't work well. Why? Forums are a way for us, all of us at the AAVSO, the international community, to communicate. And there's always somebody who's going to answer. You're going to learn from our observers, from those who are so experienced, been there, done that, and they actually are very willing to help everyone else. Also, you find a link to AAVSO Communications. This is our free e-newsletter. It comes out once a month, the first Tuesday of the month. You want to know what's happening. If you was new in AAVSO or in the night sky, please subscribe. It's just another email in your inbox, and it has really fun stuff in there. Also, if you scroll down further in our webpage, you find this nice grid of resources that, again, they're there for you. This is our observing sections, observer resources. If you want to submit data, a link on a variable star index. We do have a journal. You can read manuscripts on variable stars, manuscripts that come from the whole community, both professional and non-professional astronomers. You can actually get access to our education material. Our manuals are free to download, and they're extremely useful. And finally, if you go again to the drop-down menu, you can go and take a look at our online events. Our online events come in two different flavors. They come as webinars and they come as how-to hours. Our webinars are 2 per month. Each lasts for a couple of hours, and they're followed by Q&A. And our how-to hours is the first Saturday of every month, which is introducing a very specific practical aspect of variable star astronomy. Each hour starts with a 30-minute talk, and it's followed with Q&A. And actually, it's wonderful that individuals who participate in our how-to hours are very willing to stay as long as questions go. They're all free. You can just register for free on our webpage. And the upcoming actually how-to hour is on how to get started by building your own observatory in a budget, right? You don't want to build Palomar, but if you want to build your own observatory, how do you do that? Of course, everything is on our YouTube. So you can go to our YouTube channel, take a look at our previous webinars, or previous how-to hours. And at this point, I would like to put a plug in here. Our annual meeting is going to happen in person this year. We're getting together. It's going to happen here in Massachusetts, in next town, Somerville, the Row Hotel. We are offering a spectroscopy workshop actually before the meeting, and our meeting is on the 6th and the 7th. We will have a virtual component of the meeting simply because we found that we can connect with people all over the world through the internet, and why not? There are lots of people who want to join us and they just can't spare a weekend or 3 days to come to the meeting itself. They really want to participate virtually. You know, we live in a golden era of variable star astronomy. There's so many space and Earth-based missions and surveys that all aim to explore the night sky, and they will produce so many interesting stars that is absolutely impossible to study within a lifetime. And there are not enough professional telescopes to acquire the data that is needed and help solve some of those mysteries. The AAVSO citizen scientists are essential collaborators for researchers worldwide. If not anything else, we need more observers to acquire and help analyze astronomical data. And actually at the AAVSO, we believe very strongly that a diverse and inclusive scientific citizen science workforce maximizes innovation, creativity, and benefit everybody, especially when it comes to science. Please consider becoming a member. Even if you are not interested in taking observations, your membership is helping us get the resources to continue our work. If you have any questions, please send an email to avso@avso.org. Someone is going to respond to your request. And everything that I just mentioned is on our webpage. Everything is free. So it's a resource that is there available for you. With that, I'm going to end my presentation. I'm going to wish you clear skies and thank you for your attention. Any questions? My goodness. I left everybody speechless.
Thank you for the presentation.
You're most welcome. I
Yes,
hope.
thank you.
Any questions for me?
Yeah, well, I just I read a book by Leslie Peltier, To Know this. I think it's to Know the Stars, and I know he was very involved with the early part of last century in AAVSO. So I'm just wondering if there are any other books that you have heard about that have been written by variable star observers historically.
There is a book by Dorrit Hoffleit on variable stars. It's a little bit outdated because Dorrit's shown, I mean, her shining moment was last century, but it's really beautiful. There are lots of really interesting books. It depends on the aspect of variable stars that you are interested in. If you want, there are lots of books on variable stars themselves. You want to learn more about that. You know, I would start with our observing sections though, because there's a nice kind of outline of what the properties of variable stars are, how we observe them, how the light curves look like, what kind of cadence we need, everything you might want to know if you want to start your observing program. And one of the things, I'm gonna go on a tangent now, something that I should have mentioned. When I'm encouraging people to get involved, this is not a full-time job. You can take one data point every now and then. But you know something, this one data point you might have taken on a star might be the point that makes all the difference. And you know, one data point each person, it builds a light curve. And that light curve is so valuable for us to understand how the stars behave. We know that something is variable, it's doing something bizarre, because we have its history. We know how it behaved over time, right? Otherwise, you know, we don't have a record of anything. So back to your question, Dava Sobel's The Glass Universe, one of my favorites as well, because it provides a different perspective on the women that actually made a difference in astronomy, and they were behind the scenes for a long, long time. There are lots of books that are emerging on hidden figures, individuals, women, strong, patient, smart women who were behind the scenes and worked endlessly to make things happen. So I think I should stop here. I don't have anything specific, anything other specific in mind. For those actually, for those who want to start spectroscopy, one of my favorite books is this one. It's by my friend Ken Harrison, Astronomical Spectroscopy for Amateurs. It's an extraordinary book. I really love it. So there are lots of books from for non-professional astronomers. So, other questions? Are we ready to go out and observe?
I'd seen a written question in the margin of my iPad, but
I can read it if you want, Linda.
yeah.
For fun, what percentage of stars as observable from Earth with existing equipment would you estimate are variable stars?
Define existing equipment.
Probably, they did say probably important limitations. This is from
Right.
Jim, if Jim wants to add anything to that.
I mean, we're observing Cepheids and Miras and supernovae very, very far in the universe, right? So I don't have an answer for you, simply because we are discovering new variable stars every day.
Yeah.
Every day.
Okay, I'll add the one thing I was thinking of, that since you indicated that our sun, from at least our own distance, is a variable star because of the sunspots, that an awful lot of stars would be variable because I guess most or nearly all of them would have sunspots, but with present equipment, we couldn't necessarily see all of them. But I mean, what's fascinating is that you have mentioned so many possible categories, and you've only focused on a very few of them. And, so I guess in a secondary way, I sort of wonder from your own point of view, in terms of what is interesting in terms of research in calling a variable, how frequently something that you would call a variable that's significant in terms of further understanding and research is concerned.
So there's 3 prongs in this question. I would like to start with your first point, or 4. We can talk. I have time. You're absolutely right. Every star in the night sky is variable to a point. And this is what we learned from the Kepler Space Telescope, right? When it was out there and was observing the same part of the sky outside the Earth's atmosphere with precision that there's no way we can get from Earth. Almost every single star had active regions and spots, et cetera, et cetera. This is not something we can achieve here, right, from the ground. So when we talk about constant stars, we talk about stars whose variability is such that we just cannot detect with ground-based means, including big telescopes. The second part of your question is that, you're asking, how do we know what, out of the millions of variable stars, right, what is critical for research? And actually, that is not an easy answer, because something, depending on who you ask in the astronomical community, they're going to tell you a different star. In a couple of weeks, you're going to talk about magnetars. Magnetars was a big love of my life when I was in grad school. They're extraordinary objects with magnetic fields that there's no way we can achieve here. And yet they exist, and we don't even know how they form this kind of magnetic fields. They have star quakes, they have all kinds of crap, of nice little things there. But if you ask me what my favorite variable star is right now, I would tell you Betelgeuse.
Yeah.
Betelgeuse, it was out there and suddenly it changed Orion. And we were scratching our head for a good year to figure out what's going on. And we still do, because it's doing something different, yet different, right? When it comes to importance in astrophysics, I will not give you an answer, simply because I don't think that there is a science that is more important than another one. There is such a thing. There is a new technique, right, that helps us see the universe in a different way. For example, gravitational waves, the detection of gravitational waves 3 years ago was a breakthrough. It was something that was predicted for 40 years before, but never achieved. And suddenly we have a new tool in order to study the universe. They're cool, right? And as technology progresses, who knows? Who knows? We went from photographic plates to having something bigger than Henrietta Levy would even imagine in our hands, on our cell phones, right? When it comes to detector, we can take better pictures. So I can tell you what my favorite research field is. I love cataclysmic variables. They keep me up at night. They're doing things, no two orbits are the same. And the ones that I'm studying have orbital periods of about 3 to 4 hours. So within a night, you can see two behaviors. But I'm joking with my friends and tell them that I have a very short attention span. If something doesn't do anything important or different within an hour, I'm going somewhere else. Exoplanets are super important, right? But at the same time, pulsators, Cepheids, we're defining distances, right? Miras, big giant stars that are changing percentages of their size with time. Why? How? When? Eclipsing binaries. Without eclipsing binaries, we don't even know radii, masses, densities, everything, properties of stars. And if you put them close together and they start interacting, then they become even more interesting and much more fun. So here's a non-answer to your question, in principle, but I hope it makes sense.
I'm wondering, getting back to the observation question, for instance, you talked about being able to see the two stars of Sirius, which would be really interesting. But what would it take to do that? I mean, I've got a pair of fairly ordinary binoculars, and Sirius just still looks like a dot.
Yeah,
in the sky.
You need a bigger aperture for that, like a 1 meter class telescope, and you do need good skies.
Yeah, dark sky. Yes.
Not only dark skies, but stable skies, like a arc-second seeing, not a lot of turbulence, because it can dilute the light that comes to you. So I don't know what kind of observatory you guys have access to, but if you have access to a 1 meter class telescope, try to look at Sirius. If it has good optics, then you should be able to see it. It depends on the optics as well, right? How cool they are. If there's turbulence on the mirror, then it's been diluted as well.
Okay.
Full disclaimer, I have not seen it.
Okay.
I haven't.
So a high elevation would help, because the stars are steady when you get high up, as opposed to, my home is probably at 80 feet above sea level, but I can go observe at Tahoe, and it's thousands of feet tall there, and the stars don't move hardly at all. So you make a more accurate assessment of size comparison, perhaps.
Well, try it.
Yeah.
Yes.
Right, I know. Good to go back. I was reading that our sun has been moving out of solar minimum into going into solar maximum.
Yes.
And they're protecting perhaps a very active period with lots of things to look at.
Let's see, shall we? It went through an extensive minimum. It was an insane minimum. And we have a group of very dedicated solar observers. They're observing calculating number of sunspots. Historical facts, the AAVSO since World War II has been providing the sunspot number for the number of sunspots, etc., that is still being used to calibrate cycles, because the European sunspot number, especially during World War II, was out of the question. So we had about 100 people for a full year observing nothing and reporting zero. And I really admire the perseverance and patience. I don't think I could do that.
Yeah. Yes.
Yeah. Someone has their hands up?
Okay, yes, it's I again here. So we all hear over and over again about the implications of class 1A supernovae.
Mhm.
But this is a chance to ask, what are the sure diagnostics for astronomers of what is a class 1A supernova? Is it, simply the brightness that occurs, or is there more involved than that?
Spectrum. So pretty much it's the spectrum of the star. All supernovae have very characteristic spectra. Supernova 1A specifically don't have hydrogen and they don't have silicon in their spectrum. So these two things, and you can actually get it right away when it's bright. So when somebody discovers a supernova, the first thing they do is go take a spectrum before they take a light curve. At the same time, the light curve shape is very characteristic. It's what I showed you. So we have a lot of observers who actually take follow-up data of supernova 1As because they're necessary for distances. For distances, for cosmology, everything.
Right.
In principle, that was the technique that I discussed was the first technique that provided information of different properties of the universe. There are others right now, but each one of them is checking itself with the other, right? So they're using each other as a check. So supernova 1A is super important, very active field of science.
Great, thanks.
So the Veil Nebula in Cygnus is not a 1A, I'm guessing.
It's not. It's a core collapse. Everything else pretty much are single stars that collapse.
Yeah.
Other questions?
Well, I could ask again, when you're talking about variability for our sun, I don't know that you could see this anywhere else, but some of these absolutely huge prominences, and I think we just had one, do not seem to have cycles. And I wonder how they figure into observation and calculation.
We see more prominences when the sun's closer to its maximum, right?
Yes.
Because
yes,
the sun
but,
is in its minimum doesn't really mean it does not have a magnetic field, right?
No.
So that's one. The second one, we do see this kind of events in other stars. We just take light curves in order to detect a flare, for example. So the way that the flare looks like has a very characteristic shape. It's from a very steady kind of light curve, has a very sharp increase of the brightness of the star and a much more smooth decrease. So we know of flares in other stars, and actually there was an article, a paper not too long ago on the closest star to us, Proxima Centauri, right? That has an Earth-sized planet, and oh my gosh, are we moving to Proxima? Well, Proxima turns out to be one of the most active stars in our vicinity. So if you want to move to that Earth, take a lot of sunscreen, like a lot of sunscreen. Lots of UV radiation. It's not a very friendly place.
No.
Yeah.
Any more questions that anyone has?
Well, if there are no more questions, thank you so much for your attention. Feel free to reach out to us if you want to start your observing program. If you want to just find out what's happening in the variable star world, sign up for our webinars and how to ours. They're free. This is something to keep you company on Saturday.
Thank you so very
Thank you.
much for speaking
Yes.
to us so late in your evening.
Oh, that's
We
fine.
appreciate
I'm an
it very
astronomer.
Yes.
I'm an astronomer.
Well, that's wonderful. Thank you so very much for being with us
Yes.
tonight.
Yes,
Thank
thank you
you.
for joining us.
Thank you.
Thank
It was
you.
great.
Pleasure meeting you all. And I hope
Yeah.
clear skies, stay safe. And I hope to meet you in person sometime in the future.
Thank you. That would be
Thank you.
great.
Wonderful, clear presentation. Really
Yes.
Yes.
Thanks.
Yes.
well organized, well taught.
Yes. I'll be
Mhm.
checking out the website.
Sounds good. Well, now you know that stars throw up.
And
I
also
think of it, I can think of it in kinder terms than that, especially since we're far enough away from it not to have to clean up the mess.
Right.
You
And
have
thank
to-
you for giving us permission to have recorded this and put it on our club lecture archive so people can go back and clarify points or just enjoy seeing it all over again. Thank you so much.
Oh, you're most welcome. You're most welcome.
Thank you.
Anytime.
Mhm.
All right. Be safe, everyone.
Thank you. You too.
Thank
Have
you.
a good night.
Bye-bye.